Hello, I am Tatsuya Komatsu, and I'm engaging in foundational research on sound at Line Data Labs. The title of my presentation is Environmental Sound Recognition with Machine Learning. I will talk about Line's foundational research on environmental sound recognition. Many people might not be familiar with what environmental sound recognition is about, so I will first explain briefly about this field of research and then talk about the specific research that we are engaging in. For those of you who do not know what environmental sounds are, I will first like you to hear the actual sounds we target in our research. These are sounds that are typically heard in an office situation, and I think you have noticed that many types of sounds are included here. For example, speech, coughing, door knocking, and scream, which can be quite scary. Automatically recognizing such sounds that occur in our daily lives. That technology is environmental sound recognition. The first thing that might come to your mind when you hear sound recognition technology might be speech recognition. Speech recognition is a technology to transcribe what people say. For example, if you have this sound as input, this is a lady saying that she has never been in such a place before that is recognized by the technology. However, what is the context in which this lady is saying this? In the real world, it is not only speech, but other sounds are also present. Please listen to the sound you might hear in real-life circumstances. This might be quite an unusual case, but you might think this lady is traveling abroad. On top of what is being said, you might have also imagined various scenes from the sounds. Like this, if you hear music or sounds of lively crowds in the background, environmental sounds can tell us richer information that cannot be conveyed just by speech. Possible application of this technology include city surveillance to detect screams, shouting and sounds of glass breaking, as well as home monitoring, detecting sounds of dogs barking, talking, and sounds of home appliances. These are the possible applications. Also, automatic tagging of multimedia data on the web. This technology is receiving lots of attention because there is such a wide range of possible applications. Not only that this area has a wide range of possible applications, environmental sound recognition is also a very popular research topic. For example, there is an annual international workshop specialized in environmental sound recognition, which is called DCASE. This was also held this year. As you can see, the number of participants have been growing significantly, especially this year. The participation doubled compared to the previous year. This is also a very active field of research. This is DCASE community. They hold annual workshop on environmental sound analysis. as the increase in the number of participants show, environmental sound recognition is being researched actively on a global scale. By the way, I also participated in this year's workshop as one of the organizing committee members. This is an area that I am focusing very heavily on. In addition to DCASE being an academic workshop, an international competition like TAGO is also held simultaneously. Public data, open data, and open baseline method is used in the competition, so anybody is able to participate in this event. This competition is also contributing to the growth of this research field. One main theme of today's presentation is Line actually joined this challenge together with interns from Nagoya University and Johns Hopkins University, making use of the outcomes of last year's student internship. This is the competition we participated in. The task was to find 10 types of sounds that are heard in the domestic environment watching video clips from YouTube and Vimeo. For example, dogs barking, so, for example, dogs barking, sounds of the piano, and baby crying and the father talking while the music is playing in the background. So this was a task to recognize such environmental sounds. And as a result, we were able to come in first place. In this session, I will explain about environmental sound recognition and how we were able to win first place in the competition. Environmental sound recognition is a discipline to recognize and understand what sounds are occurring under what situation. To be specific, the acoustic signal comes in as an input, and we classify what type of sound occurred at what timing. It is a classification problem. I will explain using the data which was actually used in the DCASE 2020 competition. The target were videos with domestic sounds found on YouTube, such as dogs barking, children crying, and sounds of vacuum cleaners. We had to recognize those sounds. These sounds were all posted by users, so they were very diverse and noisy. I will now explain the background on how we can handle sound data. The data that is used in sound-related technology are digital signals recorded by microphones from wave signals in the atmosphere. This signal shown here is the same as the sound I introduced at the beginning. Can you tell which sounds are found where? It's very difficult, isn't it? The wave signal itself cannot be understood visually. You have to hear the sound in order to know what the sound is about. It is very difficult to understand something by just looking at the waveform. So if you have studied sound, it might be common sense to you that the method to analyze sound is actually to analyze the frequency. How much of that frequency element is included in a particular sound. By doing this analysis, we visualize the sound. This is the spectrogram that you get from frequency analysis. You might be able to recognize a pattern here. The location where each environmental sounds come in, it looks like this. You might be able to see some characteristics visually. You can analyze sounds more easily by analyzing the frequency, since they can be handled like images. In environmental sound recognition, the recognition model is built using the frequency characteristics. This is the general procedure of environmental sound recognition. First, we convert the input down into spectral features. By comparing the spectral features with the spectral model that has been trained beforehand, the environmental sound is recognized. You might think this is no different from image recognitions, but sounds have their own characteristics. One is the local spectral characteristics I mentioned earlier. On top of that, there's also temporal change, which is a global characteristics. So this is how the sound changes in time, and this is also a big key. And various types of sound occur simultaneously, so there is a possibility of overlap. One solution to that is source separation. Source separation will be handled in more detail in the next session. If you are interested, please listen in to grasp both of the local and global characteristics of environmental sounds. One popular method to grasp both local and global characteristics is using the convolutional-recurrent neural networks. This method combines CNN, convolutional neural network, and RNN, recurrent neural network. After taking in the local features with CNN, RNN grasps the global temporal changes. This method is used widely in analyzing environmental sounds. In the DCASE competitions, all teams except ourselves were using this convolutional recurrent neural networks method. So the explanation up till here was about environmental sound recognition in general. From here, I will explain what method we used in order to win first place in the competition. As explained earlier, the task given to us in this competition was to recognize sounds in datasets comprised of videos, which were uploaded on the web, such as YouTube. The task was to recognize the domestic sounds, such as dogs barking and babies crying, and we were competing over the recognition performance. The source of the sounds that we had to recognize were coming from videos posted by users, so they had background noise, a wide variety of characteristics, and also low-quality sound labels. One important challenge in this task was Weakly labeled training. Sounds are not visible. So that's why it's hard to annotate or give labels to sounds. For example, in case of images, if you are asked to find a dog, it is easy to find the dog and attach a label to it. However, if you are asked to find a dog barking within this sound, you cannot tell from the waveform. So that's why you need to listen to all the sounds in order to find the barking sound. To label the dog's barking sound, it is necessary to listen to all the sound. So jack label learning is being used here. Weak label is a method of learning using weak labels, like the dog is somewhere within this sound, but you don't know where exactly it is within the sound. Of course, the computer does not know which part of the sound is the dog barking. So, unneeded sounds such as the piano music in the previous data can be mistakenly learned by the computer as the dog barking. So this is a very difficult training problem. There are also other important challenges. Since all data came from the web, there might be data which is not even labeled, much less weakly labeled. So this was the problem of unlabeled data. So it was necessary to find a way to learn from unlabeled data. Also, the quality of data was very low because they were data coming from ordinary users, so the data had diverse characteristics and lots of noise. We needed a robust recognition model that could handle such low quality sounds. To tackle this, we used the method based on self-attention. We used the self-attention or transformer that was showing outstanding performance in various fields, such as NLP and voice recognition. It was the first time the transformer was applied to environmental sound recognition. In the competition, all other teams were applying the CRNN model, and we were the only team that was using this new structure model. The transformer is able to grasp the global characteristics more effectively. To apply the transformer to weak label training, we used a special token for weak label estimation as a new input. And we developed a method to handle the weak label smartly within the transformer. On top of that, we included the convolution module in the transformer's self-attention module, and we also used a network called convolution for augmented transformer, or conformer, which can capture local and global information. Next, for training of unlabeled data, we applied a method called mean teacher. In this method, we have a student model and a teacher model that share the same structure, and we apply separate noise augmentation models to the same noise and input. We then train the network parameters so that the results of both models will be as consistent as possible. This is able to increase the robustness to noise and also can extract features from unlabeled data. To increase robustness, we applied multiple data augmentations. To be specific, the first is time shifting. By artificially shifting the timing which the sound occurred, we can prevent overfitting on temporal timing. Also, by adding noise artificially, as well as masking frequency information, we can purposefully create data which has missing information. Mix-up is a method used widely in the area of images. This is creating new data by adding up two sounds together. These are the methods we applied. To summarize our method, the basic structure is transformer or conformer customized for weak label supervised training and learning from unlabeled data using mean teacher method, as well as data augmentations using multiple methods. By utilizing these methods, as we explained in the beginning, our team came first place in the world. Our performance was 14.6% higher than the baseline system and 3.3% higher than the team that came second place. The second place and below, all the teams were very close, but we were by far number one. The model used in this competition and the model to reproduce the performance we will be releasing to ESP.net, which is an open source toolkit for voice recognition. So please check it out if you are interested. Now, I will introduce some recent research activities in Line. There are still barriers to put environmental sound recognitions into practical applications. First is data mismatch by recorded devices. Second is meaning of sounds depend on the scene. Third is richer information. We also want to know where the sounds are coming from. The direction. I will show you the approaches we have taken to solve these challenges. About data mismatch, with the spread of smartphones, anybody can now record sounds and upload them. As a result, there are diverse sounds in the world because the microphones and codecs are different. This picture shows a spectrogram recorded with a high-performance device. And the other one is a spectrogram which was converted using a codec called OGG. Both were originally the same sound, but as you can see, they have totally different frequency characteristics. This type of data is very difficult for machine learning to handle. What we did is to do a classification which is invariant to device and codecs. We developed a method combining domain, adaptation, and knowledge distillation. First, through domain adaptation, we first had the computer learn the model specialized for each device. Although the specialized models excel at certain devices, the generalization performance to other devices are low. So we combined all the device-specialized models through knowledge distillation to generate a robust model that can work well with any device, and we were able to succeed in this. The next challenge is the fact that the meaning of sounds depend on the scenes or the situation. Even if it's the same sound, it may have different meanings depending on the scene. For example, in this case, shouting in a large voice in daytime will not be a problem. But if somebody shouts in the middle of the night in a residential area, that might show something dangerous is happening. So even acoustically speaking, if these two sounds are exactly the same, they mean totally different things depending on the circumstances. So what we proposed is scene-aware sound recognition, that is, recognizing sound taking the scene into consideration. On top of recognizing the environmental sound, the scene is also estimated. This is a multitask method. And the estimated scene information will be used as features for conditioning when recognizing environmental sounds. By doing so, we were able to achieve scene-aware sound recognition. As a result, we were able to lower the error rate by 58%. Error rate meaning recognizing environmental sounds that cannot possibly occur in a given scene. Lastly, I would like to explain about the research on trying to localize the environmental sounds, or from which direction the sound is coming. This is also a multitask of recognizing and localizing the sound at the same time. Here we use multiple microphones, and by calculating the difference in the time that the signals reach the destination, we use the phase information to estimate the direction. I'm sorry this might become a little bit technical, but we focused on the point that the input needed to recognize the environmental sound and to localize the sound are different. That's why we needed a mechanism to automatically distinguish what information is needed to recognize what, and to control that. We used GLU, or gated linear units, to realize this. As a result, by using this framework, we were able to increase both the sound recognition and localization performance. To summarize, this was a session about environmental sound recognition. First, I explained the method we used to win the DCASE competition. Then, I introduced more advanced activities in line, such as codec-invariant environmental sound analysis, scene-aware environmental sound recognition, and multitask problem of recognition and localization of environmental sounds. So I hope that you are interested, and I hope that you will challenge this. Thank you for your attention.